Lesson 12.3 Fluid Dynamics. Learning outcomes. First, to illustrate fluid flow. Then, to explain and use continuity and Bernoulli's equation. When fluid is in motion, its flow can be characterized into two types. First type is streamline or laminar flow, and second type is turbulent flow. Okay, now we want to talk about continuity and Bernoulli's equation. Consider that the fluid flow undergoing steady flow through the pipe is shown. For flow rate at point A1 and A2, V2 for flow rate at point 2. So, A1 is equal to rho A1, A1, V1, and A2 is equal to rho 2, A2, and V2. As we know that is a same fluid, so rho 1 is equal to rho 2. And then we can get A1, V1 is equal to A2, V2. Or AB is equal to constant, known as continuity equation. In fluid dynamics, Bernoulli's equation describes the behavior of a fluid moving along a streamline. Consider that the fluid flow from point A to point B. At point A, we have cross-sectional area for A1, and at point B, cross-sectional area A2. And at point A, we have H1, and at point B, we have H2, which is the pressure at point A, P1 is more than pressure at B, P2. For this case, the fluid flow in steady flow. So we consider that V2 is equal to V1 is equal to V. Lesson 12.4 Viscosity. Learning outcome for this lesson is A. Define viscosity, B. State and use Stokes Law, and then sketch the graph of velocity time Vt to explain terminal velocity in liquid. Viscosity is the quantity that describes a fluid's resistance to flow. It exists in both liquids and gases and is essentially a frictional force between different layers of fluid as they move past one another. In liquids, the viscosity is due to the cohesive force between the molecules, Meanwhile, in gases, the viscosity is due to collision between the molecules.
And timing the sphere to cover that known distance, we could work out the velocity of the sphere. So, making the simplifying assumption that we can ignore upthrust, the forces acting on the sphere will be its weight acting down and the viscous drag acting up. If the sphere moves with its terminal velocity, v sub t, the weight must be equal to the viscous drag. Don't forget this is ignoring upthrust. He found that the viscous drag was given by this term. This formula is provided on the datasheet. Stokes' law allows us to work out the units of the coefficient of viscosity eta. Here we have the Stokes' law expression again, and rearranging for eta we find that the coefficient of viscosity is equal to the force over 6 pi rv. The force will be in newtons, the radius in meters, and the velocity in meters per second.
Stock force N is given by Stokes' law. Fs is equal to 6 pi eta rv. Now we see graph velocity time Vt to explain terminal velocity in liquid. Okay, you can see graph V against T, velocity against T. When a sphere falls in a viscous fluid, its velocity will increasing until it reaches a maximum velocity. Then it continues to fall with this constant maximum velocity, which is known as the terminal velocity or Vt.